We'll wait for a few minutes for others to join.
Good evening, sir.
Yeah, good evening, Santosh. Am I audible?
Yeah, you are audible. Audible.
Okay. I'll start in a few minutes. Let others also join.
Okay, okay.
So are you able to solve the assignment questions?
Today's, sir,
I'm asking that, are you able to solve the assignment questions now?
sir.
Uh, are you attempting the assignment questions
Yes,
provided
sir.
by the
I am
NPTEL?
attending, but your volume is very very low, sir. I can't hear. Your volume is very. Your voice is very very feeble, sir. I can't hear.
Just a second. Now, is it? Uh, now is it clear?
Yeah, sir. It's visible. Yeah,
It's
sir.
better. The
Yeah. Better,
oh,
better, sir.
okay. Okay.
Sir, today's session, what are you going to teach, sir?
So we'll start with analysis of cycles and then combustion, actual combustion in the spark ignition engine, how it happens.
SI
Okay.
and
We'll take.
CI. SI and
Yes.
CI.
Yes.
Okay, sir. Thank you. Is there is
So
any analytical question in this subject, sir? It's an analytical subject, I think so. IC and GT.
no, we have done so many numericals. It's not analytical subject.
No, sir. I'm asking. There is a problem. Problems are here, or I am asking.
Ah, okay. So no, I don't think there are any theorems related. It's not like a thermodynamics that you have to prove any theorem.
Okay.
It's more
Uh,
of an application based course.
okay, sir. Another doubt is in NPTEL exam, they will ask only MCQ or they will ask problem also.
It can be mix of both as well.
Okay. I'm asking just. Okay.
Yeah,
They will ask only
but
basic problem to
but
solve.
they will ask whatever has been taught by the professor, discussed in the tutorial. That's
Okay.
the thing,
Okay.
and all the topics which have been covered.
Okay, sir.
And as well as you do the assignments, you get the solutions for the assignments. So similar problems will be there.
Okay.
Yeah. So you are able
Okay.
to do the assignments.
Yeah, I'm able to do, and I will see few tutorial videos, and I will see often. I will see your
Okay.
tutorial videos in the NPTEL with Varnit
Yeah.
in
Yeah.
YouTube channel.
Yeah. Okay.
Okay, sir. Thank you.
You are currently in which university?
I'm in SRM, South
SRM.
India, Tamil Nadu. SRM
Okay.
Trichet campus.
And you are in which year currently?
Fourth year, 8th semester.
Okay.
Sir, okay, thanks.
Okay, then let us start. Let me just share my screen. Maybe others will join meanwhile. Wait. Okay, so right there. Okay. So welcome to the week 6 tutorial for the course IC engines and gas turbine. So in the previous tutorial, we finished up with the actual IC engine working. Okay. And then we did a numerical related to it as well, a very detailed numerical. Now today, let's start. Let me share my screen. I hope my screen is visible. Is it?
Just visible.
Okay. Okay. Thank you. So let me just type it. Someone else is also trying to join. Wait. My camera is not visible, I guess. Okay. Now it will work. So analysis of cycles. So we have seen all the cycles so far, the auto, diesel and dual cycle. Okay. So let us see which cycle is better when compared. Okay. What was the necessity of bringing the cycles? Eventually, we need to have an efficiency, higher efficient engine always, which will help us to provide more efficiency. So let us say we have a, let me plot a pressure volume diagram. Or let us say we have, is my video visible? Santosh, can you confirm me, is my video and audio clear?
Yeah, sir.
It's okay.
It's
Okay. Okay. Thank you. All right. So I was saying that let us have a make a PV diagram of a diesel cycle. We have seen this lot of time. So from 1 to 2. Let me, then a constant heat addition, constant pressure heat addition, and constant volume heat rejection. So these are the processes. We know that the compression ratio for a diesel cycle is higher, like from 16 onwards, whereas the compression ratio for an SI engine, that is auto cycle, is lower, 6 to 12. Okay, so obviously if the compression ratio is higher, then the swept volume will also be higher for a diesel engine. Okay, so let us say this is our swept volume from V2 to V1. Okay, whereas for if I want to make an auto cycle, our swept volume will be less. Okay, so eventually our auto cycle will start from here only 1, but the compression ratio is less, and then constant volume heat addition, expansion, isentropic expansion, and constant volume heat rejection. So this will be your auto cycle, 4 dash and 1 dash. Okay. So if we see that, we always know that area under the graph is provide us the net work done, and higher the work done we get, from the net work done we get, the efficiency of that cycle is more. Okay, so efficiency is nothing but work done net to that of heat added per, okay, heat added at constant volume or pressure, whatever the process is. Okay, so we see that the work done net, let us make it in a form of a ratio, work done net, and we know that heat added is nothing but work net plus heat rejected. Okay, this we know from the first law. Net heat interaction is net work interaction from the thermodynamics. So we can write work done net plus heat rejection, whether it's at constant volume or pressure. Let us say rejection is always at a constant volume. Okay. Now let's divide the numerator by work done net. So it will be heat rejection at constant volume to that of work done net. So if we say our diesel cycle has a higher work net, so that means overall this ratio will be less. So if this ratio is less, then overall the whole ratio of this will be higher. Okay, if denominator is less, then we can say that our whole value or the ratio is higher. That means our efficiency is higher. So we are getting a higher work net in diesel, since work done net is higher in diesel cycle. Therefore, we can say that efficiency of a diesel is greater than efficiency of a dual is greater than efficiency of an auto. Okay. Now, question might be asked that dual has a less mid compression ratio, 16 to 22, whereas a diesel engine has higher than 22. Okay, and auto has 6 to 12. That's why. So if I'm saying this is auto, this is diesel, and if I want to make dual as well, so compression ratio will be till here, then heat addition at constant volume, heat addition at constant pressure, and then finally this will be your complete dual cycle. Okay, so highest work done we are getting always, the net area we are getting from the PV graph is of diesel cycle compared to dual, then compared to auto. Okay, let me write in a sequence way. So this is dual and this is auto. Okay, diesel, dual, auto. All right, I hope this is clear that diesel engines are more efficient. Diesel engines are therefore diesel engines are more efficient. Okay, now the question is that there is one exception, which is a hypothetical exception. What do I mean by that is, if I make a PV plot, why it is not making PV plot, and I say that a special case for same compression ratio. Currently, we know that compression ratio of a dual cycle diesel is higher than dual than auto. But if I say if I have three engines, diesel, dual, auto, and all of them have the same compression ratio, which is not generally feasible for same R is compression ratio, for same compression ratio. Okay, let us make the cycles. So for same compression ratio, if you try to plot it, first let us plot auto. 1, 2, 3, 4. So this is auto cycle. Okay, auto. Then a dual cycle will come, because compression ratio is to be maintained. So that means your swept volume should always be same. Okay, all will have the same swept volume. So then heat addition at constant volume, then heat addition at constant pressure, then expansion, and finally rejection. This is your dual. Okay, and finally your diesel. Finally your diesel will come. Compression from 1 to 2, then heat addition at constant pressure, then expansion, and then finally heat rejection. Okay, and this is your diesel. So this is the only case, if you observe in all these three graphs, that auto is having a higher area. And if area is higher for an auto, that means work net is also high, and that means efficiency is higher. Okay, although it is practically impossible. Practically impossible. Okay, but this is the only case where efficiency of auto is greater than efficiency of dual is greater than efficiency of diesel. Only when the cases of same compression ratio. Okay. All right. Any doubts in this? So we understood that diesel engines are more efficient, always efficient, and but if one case comes when the compression ratio is same, then auto engine cycle is a better cycle. Okay. Now let us come to the combustion in the SI engines. Combustion in SI. This is a very, very important topic, so please listen it very carefully. Okay. And if you have any doubts at any point of time, please stop me and ask. Just hold on. Combustion in combustion in spark ignition engine. Okay, so I'm talking about currently Otto cycle. Okay, so let us see, and we will see both the cases for actual as well as I'll make first graphs for both of the cases, actual and ideal. So we have discussed how the actual engine works. So if I say this is my pressure volume plot for a theoretical case. Okay. So first compression happens and no, this is not volume, this is crank angle. Okay. How with the crank angle the pressure changes. Okay. Crank. So first is, let us say this is center is at 180 degrees at one of the position. That is from bottom dead center I'm starting. The compression stroke I'm talking about. The first case is compression is happening. Okay. Compression is happening. Let me make this a dotted line. Okay. So at some point compression happens, eventually pressure is going to increase. Okay, with the crank angle. It's going to be a linear relation. Okay, with some slope. Let us not go into that, but let us say that process A to B, point A to point B is where compression is happening. Okay, isentropic compression. Okay, so let me write here compression. Okay, compression. Then we add, then what we do at this instant itself, we provide the spark. We provide the spark, and at that itself at constant volume, because of the we are providing the spark, the heat get added. Okay, at the constant volume. So at that crank angle itself, we are saying that our heat has been added. Let me join this. So from B to point C, let us say this is our point C. Okay, this is our point C. So what happened? We provided spark begin as well as ignition also started. Heat has been added. So spark has also been provided, and at that itself, the fuel has been burnt immediately, and the ignition has happened. Ignition has happened. And finally, at C point, spark is also ended, and ignition is also ended. The whole fuel has been burnt, spark ended, and ignition also ended. Also ended. E for ended, B for begin. Okay, and finally, expansion stroke happened at the. So initially, during the compression stroke, the crank moved from the piston moved from BDC to TDC. That is 180 degree till it covered, and then 180 degree of the stroke it covered, and then finally Heat has been added at that instant itself, and finally it comes back to the expansion stroke. Okay, so that means the crank angle is further moving and expansion is happening. So here expansion happens. Okay, and at that instant itself, heat is rejecting. So this is point D, and from here to here, the heat get rejected. Okay, heat rejection. Heat rejection at constant volume. Okay, and here expansion ends. Okay. All right. So this is the cycle. This is heat addition. Let me write heat addition at constant volume. Heat addition from B to C. A to B compression happened. B to C heat addition at constant volume happened with the crank angle. C to D expansion happened. So this is till here expansion. Okay, isentropic expansion, and then from D onwards, you can say heat rejected. Heat got rejected. It got rejected at constant. So this is an ideal scenario. But in actual cycle, we have seen that in our previous tutorial that heat get added before some degree of reaching the top dead center. Then heat get ignition begins after that. Then after that, the expansion happen and heat is still adding or spark is still happening till after some degree of the top dead center. We have seen all these processes. Okay, and I'll explain how the ignition thing takes place in. We have still seen that how the spark begins, but we have not seen how the ignition begins and how the fuel get combustion. Okay, okay, all right. So let us make another plot here itself. So this was a theoretical case. Let us make a actual case scenario. Very important diagram. Pressure volume, pressure theta plot. Okay, with the crank angle. Pressure theta plot. So let us say again we started from position A as we started from here. So this is a position A. Let me once make the graph and step by step I'll explain. Okay, what happened. So let me make the graph first. Okay, but no, it's not like this. Okay, let's make step by step over here. Okay, let me make 180 degrees here. Again, crank angle. We have to be very patient when understanding this because I'll be explaining each and every step in very detail now. Okay, I hope I'm clearly audible. Can anyone confirm? Santosh, Rakhi, Swara, am I audible?
Yes, sir, you are audible.
Okay, all right. So again, we say that our ignition compression starts as it started before in the ideal scenario. So this is a actual. So from point A, compression start. Let us say compression happened till some point. Compression happened till some point A, and that point is A, small a. Okay. So from capital A to small a, compression started. Okay, compression started. So this is the first stage of the combustion. First stage of the combustion, I'm going to explain how the first stage of the combustion starts. Anyone? Okay. Yeah. So I'm going to explain that the first stage of the compression started. First stage of the compression. Let me write actual cycle. I'm now clearly explaining about the actual cycle in the spark ignition engine combustion. Okay, actual cycle. Okay, so first stage of combustion. First stage of combustion. First stage of combustion. So what happens when I'm saying when the sparking begins at small a, okay? Then the contact takes place between the spark and the nearest fuel particle, okay? Nearest fuel particle layer. Because you have compressed the fuel, the pressure and temperature has already been raised in the cylinder, piston cylinder arrangement. And the spark is just near the, in touch with the nearest particle layer of the fuel particles, okay? Then what happens? Then at that point, the temperature of the fuel changes from flash point temperature to a fire point temperature. So what is happening there? The chemical action begins at that point of time and it liberates heats, which is then spread to the next fuel particles because of the presence of temperature difference. Because your spark is at a higher temperature and compressed fuel is at a lower temperature. Comparatively, relatively, I'm saying. Although fuel has been compressed and reached a temperature of T flash, but as soon as you provide the spark, your T, it changes from T flash to T fire point. Okay, T flash to T fire point. So let me first write it here. This point A is nothing but your sparking begins here. Point A is a point where spark begins. S stands for spark begins. Okay, and till A, our compression is happening. Okay, till A, our compression is happening. C stands for compression is on, and the piston is moving from bottom to down. Okay, that is the arrow it stands for. Okay, here also in the left graph, C stands for compression, and here expansion was happening. Okay, so C is compression is happening, and at point A, which is, let us say, we can say around 6 degree before top dead center. So let us say this angle, don't go on the scaling that this is so much 6 degrees. Let us say it is 174 degrees now. 174 degrees. Okay. Okay. So this is 174 degrees and the spark has begun. So crank is at 174 degree before top dead center and the spark has begun. So first stage of combustion says that when sparking begins, let me write, when sparking begins, that is your point A, okay, then contact takes place between spark and the nearest fuel particle layer. Okay, that is your temperature rise from T flash to T fire, and we have discussed what is flash temperature, fire temperature, and then
Hello,
the
sir.
chemical. Yes,
Hello.
am I audible?
Sir, in first stage of yeah, you are audible, sir. I am audible, sir. Can you hear?
Yes, yes, yes.
Sir, no, sir. First stage of combustion. Can you scroll back to first stage of what you have been you was written when sparking begins? A first point A, then contact take place. What type of contact take place, sir?
So the fuel is being compressed, and the spark is also spark plug is there, right? So spark plug
Okay.
provides a spark, and that spark and the fuel start to have a contact. Okay.
Okay. Okay, sir. Okay, thank you.
So
Fuel and spark will be contact after the contacting the combustion take place.
no, not combustion take place. The temperature of the
Uh,
first layer of the fuel, the nearest layer of the fuel, the temperature rise from
okay,
flash to fire. Till now,
okay,
combustion has
okay,
not taken place. Combustion will take place.
okay,
How it will take
okay.
place, that is
Pre,
I'm going to explain. Then the chemical action
okay,
begins.
uh,
Then
okay. Okay.
Chemical action begins and it liberates heat, which spreads to next fuel particles, to next layer of fuel particles. Okay. Because why? Because of the presence of temperature difference. Because of temperature difference. Because the first layer has already got some temperature, the second layer has not still got. So there is still a temperature difference. So that is why, because of the temperature difference, the fuel gets the heat. So let me show diagrammatically also this thing. So we have seen this fuel, how the fuel looks in few initial tutorials. So outer layer is covered by hydrogen, inner layer is covered by the carbon, okay, or hydrocarbon. So basically, so so let us denote the fuel. The inner is CXHX, hydrocarbon is there, CXHX. Okay, it can be any chain, and there is a spark. Okay, so there is a first layer of the fuel particle. Chemical action begin. Chemical action. So it was at red because of the compression. Till here, the compression has happened. This is a point A till where compression has happened. Okay, chemical action. Okay, and then let me again make a. And then what happens? This fuel, the first layer of the fuel, liberates heat. Okay, and to the next fuel particles. Okay, so let me make it through some another color. Let us say now it has burnt. Okay, the first fuel has been burnt. Okay, so temperatures are varied from T flash to T fire. Okay, T flash to T fire. Here, what begin? Spark begins, and here ignition begins. Now ignition will start. Okay, so as soon as from A to a point small b, let us make now point small b. Now ignition has started at point B. From A to P, the ignition has started. Okay, because of the presence of spark. So here at point B, ignition begins. So from this range to this range, if I say to some crank angle, here compression is also there, and because still the piston has not moved to TDC. TDC is at 180 degree. TDC is at 180 degree. Still compressing also, plus sparking has also begun. Okay, plus sparking has also begun. Sparking also started. Okay, so between A to point B, compression is also happening and sparking is also taking place. We have seen this thing in the previous tutorial where I explained each and every step of the actual PV diagram. Okay, but now we are relating with the crank angle. Earlier we were relating to the pressure volume. Okay, this is TDC. TDC. All right. So ignition begin. So ignition begins. So this was the position A. Oh, did I? Yeah. So this was a position A, and this is a position B on the graph. Okay, position A and position B on the graph. All right. And what is happening in the meantime? There is a rise in the temperature of fuel particle. There is a rise in the temperature of fuel particle because of the heat transfer in the form of radiation, in the form of, because temperature is very high. So this moment of heat transfer from nearest fuel particle, that is the nearest to the spark plug, to the different region of the fuel. till the other end of the spark plug. Okay. This movement of the heat transfer is basically called as propagation of the nucleus. Propagation of the nucleus. Let me write and then you will understand. Let me first write what I'm trying to say. Okay. In the meantime, there is rise in temperature let me make a figure also parallelly here. There is a rise in temperature of fuel particle because of heat transfer. And what is the mode of heat transfer? Here is the radiation. There are three modes of heat transfer: conduction, convection, and radiation. There can't be conduction, it is not solid. There can't be convection because there is no density difference in the fuel. Fuel is same. So there is a radiation between the particles is happening at intermolecular level. Okay. So in the form of radiation. In form of radiation. Okay. And this moment of heat transfer, this movement of heat transfer from nearest fuel particle to spark plug, nearest fuel particle, the particle which is nearest to the spark plug, I am saying, okay, nearest fuel particle to spark plug. To different region, one is the nearest fuel particle to the spark plug to the different region till other end of spark plug to different region till other end of spark plug is known as propagation of nucleus. Okay, propagation. Let me explain this diagrammatically. Okay, so we have a spark plug here. Okay, I'm showing the top view of the cylinder. So this is a top view. These both are top views. All these are the top views. You are looking the cylinder from the top. Okay. So what is happening? We have nucleus of the fuel at intermolecular level, if I say. Okay. So let us say. Okay. Let us make like this. And in each nucleus, there are fuel particles. So this is the fire point fuel particle. So I'll make from the same color. So this was a fire point fuel particle, which was nearest to the spark plug. Okay, these fuel particles were nearest to the spark plug. And then this nucleus has other, no. So this nucleus is still at the flash point temperature. So same, I'll use the red color. Red color. These are at red color. Okay. So the nearest to the fuel particle is at fire point temperature. Now this will provide propagation, heat transfer because of the temperature difference, and that leads to a radiation mode of heat transfer because the radiation mode of heat transfer. And when this burns, suppose this one burns, then this will again provide the propagation. Then if this one burns, this will also provide the propagation. So that is how a propagation of from one layer to another layer is happening. Okay, and this is suppose it's happening at some angle that is 6 degrees before TDC. Okay. All right, propagation of the, so this is at 174 degrees. Let me write here at 6 degrees at 6 degree before TDC, where the first layer got burned, and from there, from 6 degree to VDC, it happens heat transfer. Let me use some another color. So this is spark plug. This is the top view. Let me write top view. Okay, top view. I'm showing. This is also a top view. Now you will understand. Heat transfer due to chemical action. Let me write this as well. So this propagation is happening because of heat transfer due to chemical action. Okay, heat is getting transferred and propagation of this nucleus is happening. Okay, and the mode of heat transfer is radiation here. Okay, now the ignition has begun. We have reached to the stage B, that is suppose 2 degrees or before the 2 or 4 degrees before the top dead center to reach. Okay, let us say 2 degree before the TDC. So let me write here 178 degrees. Okay, so don't go on the scaling. I'm saying the gap can be different. This 174, and you assume that how. Don't go over the scaling. That's why I'm writing the values there itself. Okay. All right. So till here, we have understood that ignition has begun, and now the propagation of the nucleus is happening. Now what is happening when whole of the fuel has got a fire point temperature? So that means now fuel has some self-ignition temperature, suppose of 120 degrees Celsius. I'm taking an example, random example, 120 degrees Celsius. And I'm currently sitting at 118 degrees Celsius. Now I'm very near to my self-ignition. Okay. As soon as I get self-ignited, I'm going to burn. Okay. So when the temperature is equal or greater than the self-ignition temperature inside the cylinder, the fuel then at that end of the chemical reaction, the nearest fuel particle will first ignite and the first flame front will form. First flame front will form at that point of time. Okay. Let me write the point here. Then you will understand. When temperature is equal to or greater than self-ignition temperature of the fuel, then at end of chemical reaction, nearest fuel particle will ignite and first flame front is formed. And first flame, I'll explain what is flame front, is formed. Okay, let me make it diagrammatic form. Okay, let me again, that is why I'm making a color code same. So in both this, if red is at this position and purple is at this position, so that when you again go back and see, you can understand. Okay, so okay, again I'm making, and this was your spark plug. Okay, spark plug. Now what has happened when the temperature has risen up? Earlier we were at this stage 6 degree before TDC, and then we reached to a stage of 2 degree before TDC when the fire has happened. Now chemical action has completed, fire has happened, and fire and self-ignition temperature are very near, like 118 degrees and 120 degrees. Both are at very near. At that instant, simultaneously, what will happen? The fuel will try to ignite. Okay, the fuel will try to ignite. and a flame front will form. So earlier this layer, which was near to the spark plug, it was at T fire point, but and it was propagating the heat through the mode of radiation heat transfer. But simultaneously, this was also getting burned. This layer was also getting burned, and it was getting ignited, I mean to say. So what I'll do, I'll make a small fuel particle that was from the nucleus is getting ignited. Okay, ignited, and it is also parallelly propagating the heat transfer to the particles which are at the other point of the nucleuses. Okay, that were at flash point temperature. That were at flash point temperature. Okay. They were also propagating. Let me use what color I used. Purple. So they are also propagating the propagation of the nucleus. Okay, and this ignition form a band that is nothing but your flame. A flame was formed, and it was the front. Very first flame was there, which is called as a flame front. Flame front. Okay, and it happened 2 degree before TDC. At 2 degree before TDC, that is at 178 degrees of the crank angle. So this is your position B. This was your position A. Let me write. Let me use some another color, green color. So this was position A. This is at the rate, and this is A. Okay, and this is position B. This is position B. Okay, but if this is an actual cycle which we are dealing, but if I say what is happening in the theoretical cycle which we made here, it was happening at the same instant. That means it has already reached the TDC. It is not 2 degree before TDC. It has already reached the TDC of the crank angle. So if I want to make parallelly for, this is an actual one. So let me write actual. If I want to make for the theoretical one, so already whole of the fuel is already burned, because whole of the heat has been added at that instant. So I'm making a mean of showing off all of the fuel particles. Okay, and this is the at TDC, at TDC, but which is not physically possible. Okay, we have seen this thing. Okay, so here what has happened, basically temperature of fuel is greater than equal to T self ignition, or you can say T fire. Both are almost same. Okay, both are almost same. So you have to visualize that at same instant 2 degree before TDC, just from point A to B, sorry, 6 degree. So at point A, the spark began. There was a chemical action where temperature raised for first layer of the particle from flash to fire. Then at that instant, it is propagating the heat to the other particles also, and it is also getting ignited itself. So this is the point B. Okay, that is 2 degree before TDC, and because of that, the flame front has been formed. Okay, and this flame front is there. So let me write here first. So because of that, eventually the pressure and temperature is going to rise. So the pressure and temperature going to rise. So here, sorry, I should have made till some point before maximum situation. Okay, so let us say till point here to here, this is a point C, suppose C is there. Okay, so what was the first stage of the combustion? Basically, the first stage of the combustion is increasing the pressure, temperature, how the ignition is happening, how the temperature is from flash to fire, and then the fuel got ignited because the self-ignition temperature was greater than the fuel temperature inside the cylinder was greater than the self-ignition temperature. Okay, self-ignition temperature. All right. So here, combustion plus, let us say point T. This is a point 2 degree before. Oh no, 2 degrees there only. So this is a point where, let me make, combustion plus sparking is still happening, as well as ignition has also started. Okay. So combustion plus sparking plus ignition has also started. Okay, has also started. Now let us see in another diagrammatically form as well. But let me write one more point here, that what was there happening, that from T flash to T fire, there was a chemical action. So basically this was a time from A to B, okay, from position A to position B. Okay, so this was nothing but your ignition delay. This is called as ignition delay, or you can call as chemical delay, or you can also call it as preparatory phase. Okay, this is your time, the chemical delay. You can also write its definition as total time taken from beginning of total time taken from beginning of sparking to beginning of ignition to beginning of ignition is termed as ignition delay. Ignition delay, okay, or chemical delay or preparatory phase. Okay, in SI engine. In SI engine, there is a different story for a CI engine that will go in that. Okay. Now let us see in the diagram form also from top dead center and front view. I'll make the parallel diagrams for explaining the first stage of the combustion. Till what has happened till the first stage of the combustion. Okay. Someone is trying to join. Okay. So let me make the diagram where I'm explaining the first stage of the combustion once again. Carefully understand. It will give you a recap. Okay. Let me make one more. Okay. First stage of the combustion I'm going to make. And this is a cylinder I'm going to make. So the above is the top view and are the front views. Okay. So what happened? Here we had a fuel. So color code I'll make the same. And there were just, sorry, I should have used orange color for spark plug. Spark plug. It has nearest fuel particles. Those were at T flash and had other particles in surrounding as well. Okay. If I say from this situation, this is your spark plug. This is your top dead center, TDC. Okay. This is your piston at 6 degree before top dead center. This is your position A. Okay. The piston is moved from bottom to top okay, during the compression. So here spark has begun. Spark has begun. Okay. So T cylinder is greater than the temperature is already going to be increased. So we have seen this diagram in the previous one, and here parallelly the propagation of the nucleus will also start. Okay. So this is 6 degree before TDC, and 2 degree before TDC, let us say the piston is further moving up above in the actual engine working. TDC, again I'll make the spark. The first flame front is already formed. If you see from the top, the first flame front is there, which is already there, and it is surrounded still with the fuel particles that are at a flash point temperature, and the propagation is also happening. Okay, propagation of nucleus is also happening. Okay, and this is a position where the piston has moved at point B, which is at 2 degree before TDC. 2 degree before TDC. Okay, so if I see from front how it's going to look, so there is a flame front has been formed, which is near to the spark plug, and rest other fuel particles are still getting compressed and are at T flash point temperature. Okay, and parallelly it is also providing the propagation of the heat. Okay, propagation of the nucleus is still happening. So I've used the same color code so that you guys don't get confused. And here ignition has begun. Let me write. Ignition also got begin plus, let me write first spark and then ignition. Spark begin plus ignition begin. Okay, at point B. Spark is still happening. Spark has not stopped. Till here, any doubts? Do you have any doubts understanding this part? If I want to see what will be the time between A to point B, that is your chemical delay. This is your first stage, basically. Let me, from this position to this position, this is your first stage of the combustion. First stage. Okay. And if I want to calculate a time for this, time from A to B, so how many angles theta by omega? Okay. If I am saying that my piston is like crank is moving at 2400 RPM, so theta is nothing but from 6 degree to 2 degree, that is 4 degree changes there. Okay, 4 degrees into pi by 180, and 2 pi n is 2400 by 60. So if we calculate this, we are getting 1 by 3600 seconds. So it's very fast. 1 by 3600 second. And this is nothing but your chemical delay. Okay, this is your chemical delay. Okay. Now let me write propagation of the flame front. About the propagation of the flame front. And what is flame front also? So line joining the ignited fuel particles at same instant of time is known as a flame front. Okay. So when we saw here, this was a line joining at same instant of time. Okay. All of the particles joined together. So let me write line joining ignited fuel, and ignition will happen when temperature in cylinder is greater than the self-ignition temperature. Fuel particle at same instant of time is known as flame. Let me use same color only. Purple I'm using is known as flame front. Okay, is known as flame front. There is one other definition of end charge. Let me write that also. end charge. Let me use another color for this. I'll tell that what is end charge. It is the air fuel mixture at the other end of the spark plug. It is air fuel mixture AFM at other end of spark plug. Okay. Let me show it diagrammatically to you from the top view again. So we had this top view. We had a spark plug. Okay. We have fuel that has been ignited already. A flame front is formed, but still the fuel is there in the cylinder. So the fuel which is to the other end of the spark plug. Okay. So this is still at flash point temperature, and this is your end charge. Very important role it's going to play. I'll explain how. End charge. Okay. From it's basically our air fuel mixture only. AFM. Okay. So if I show you in another way, so this was your spark plug. Okay. This was your first flame front, and the remaining fuel that was toward this side. And charge. I hope, I think noise is coming. Is the noise reduced now? Hello, can anyone confirm?
Yes, sir.
Oh, okay. So is still noise coming from my background?
No.
Okay. Thank you. So this is basically your end charge. Okay. So I'll explain what is it's basically your air fuel mixture at the other end of the spark plug. Okay. Now let's come to the second stage combustion. So we have understood the first stage combustion when we started this. Now let's come to the second stage combustion. Second stage combustion. If at any point my voice is feeble or not audible, please immediately point me out. Okay. So after the yeah, after the formation of the first flame front, the heat liberated ignites the nearby fuel particle. Okay. So first flame front has been formed. Then the heat that has been liberated by the ignition of the first flame front, it ignites the nearby fuel particle, and another front will form, flame front will form. And it appears that it reaches to a new position. Okay. So first flame front formed, then it ignites the other flame front, another nearby fuel particle layer, it forms the flame front. Then this chain goes on. And it seems that the first flame front has shifted its position, because first will ignite, it will disappear. The second will ignite, it will disappear. Third will ignite, disappear. So what is happening? It seems that the same flame front is propagating. Okay, but it is not the same set of fuel particles. It's different set of fuel particles. Okay, and this is known as the propagation of the flame front. Propagation of flame front. So after, let me write. After just let me one thing I didn't mention here. So this was 180 degree. I miswrote here. This is not 180. This is oh, thankfully I have an undo option. Yeah. So this is 180 degree till T. Okay. 180 degree. Okay, that is your TDC. Okay. From A to B, then B to T. T was your TDC. I made the diagram here, right? Which one? This one at T. 2 time is T. Okay, time is T. That is 2 degree before TDC. So that is 178 degree is still here. This is 174 degrees for A. For B, it is 178 degrees, and at one T point, it is 180 degrees. You will understand now. Further, it is going to also increase the pressure temperature. Okay. All right. So we were here till T. I was writing about one point. After formation of first flame front, heat liberated ignites the nearby fuel particle okay. So you are able to understand that we have reached till TDC now. So till TDC, the first stage of propagation, first stage of combustion has happened. We are talking about the second stage. So ignite the nearby fuel particle, and another flame front will form, and it appears like it reaches to new position. And this forward motion of flame front is known as propagation of flame front. Propagation of flame front. So if I show you diagrammatically now, this was your spark plug. Okay. So first flame front was here. Then this one got ignited, provided the heat to the other one. Second flame front formed. Then third flame front formed, and so on. Okay. So this is basically your propagation of FF. So I'll write FF was propagation. Okay. So this was a position which was at point B in the graph, and this will be some position. Let us say point D. I'll make in the graph. Don't worry. Okay. Okay. If I show you again from a top view, let me again make a diagram. So I had a spark plug, and I have flame fronts forming. Okay. And this how propagation is happening. Okay. So if I say this point was point B, so I use 4 no, so I'll use one more. This will be position of point B. Okay. All right. If I show you from the front view also how this will look, because visualization is very important in this. Okay. This was your spark plug. So basically your flame fronts were like this, like this. Okay. And this is how the propagation was happening. Okay. So again, if I say this was point B, this will be point T. Okay. And this is a 2D view. If I want to show you a 3D schematic view also, let me show you a 3D schematic view. A cylinder is there, look like this, a piston cylinder. Piston is like this. Okay. So spark plug is something like this, and these will be hemispherical frame fronts. Okay. Okay. These how it looks like. Okay. I hope you all are able to visualize now what is happening. This was point B again. This is point D. So these are hemispherical. Flame front, three-dimensional shapes. Okay. I hope you are able to visualize it. It's a very difficult thing to, but okay. So what has basically happened? The this was at a position where it has gone. Yeah. The propagation of the flame front has started. So that means till point T, where was the point T? Yeah. So from point B to point T, till 2 degree before, or from point A to point B, we had our ignition begins. From point B to point D, okay, we have uh, compression, then spark, then ignition also was there. Okay, it reached the TDC position. It reached the TDC position. Okay, and then finally, from till the TDC position at 180 degree, then the first flame front was formed. Now the ignition of the flames are happening from one to another, second to third, third to fourth. That is propagation of flame front is there. So fire is forming. That means your temperature is still going and pressure is still going to rise inside the cylinder. That's why I made it till point C. Point C. So that is nothing but, let us say, 4 or 2 degrees after TDC. Okay, let us say till 4 degree after TDC. So this is a position that is 4 degree, 184 degrees. This position. Okay, till point C. And still the expansion, then after that expansion is still happening. We have understood that expansion still happens. So this was where the expansion started from this. Sorry, let me make it a bit better. Okay, point C. So this is 184 degrees, let us say. So here expansion has started, which is going to down, piston is moving downwards, plus spark is still there, plus ignition is also there. Okay, expansion is happening, not compression. Now, so C I have removed. Compression happened till TDC. Now expansion has started, spark is still there, and ignition is also there. Okay, and pressure temperature has risen. Then it will rise till some point, and then it finally drop down till point D. Let us say this angle is nothing but 6 degree after TDC. So let us say this is 186 degrees. And here, finally, your ignition ends. Ignition ends. So from C to D, expanding, it is still expanding downwards. Plus, sparking has stopped, but ignition is still happening. Okay. And ignition finally ends at this point D. Okay. So let me write ignition ends. All right. That is, let us assume it's 4 degree. And then finally, heat will reject at constant volume. which is not again feasible in actual diagram. Some heat rejection will take place till movement will happen, which we have seen in the previous tutorial. So let's make somewhat like this. Okay, till final point D. So it started from A and ended till point D. Started from A, ended till D. Started from A, ended till D. Okay. All right. Ignition ends. And here only expansion will be left. The cylinder piston is still expanding. All right. So let me again make one figure which is talking about 4 degree after TDC. This is a spark plug. Okay. The flame front is, let us say, till here, and some end charges remaining. This is a position at 4 degree after TDC. So this is your position number C. Okay, 4 degree after TDC. And finally, we have spark plug where whole of the fuel is almost ignited and ignition ends here. This is ignition ends at 6 degree after TDC, and this is your position number D in the plot. Okay. I hope this is clear. Now we will come to the concept of abnormal combustion, which is also called as knocking, which leads to pinging. Okay. Let me write. I hope there is no doubt. Is there any doubt? Please say yes or no. Santosh, any doubt? No doubt. Okay. Am I audible? Hello? Am I connected?
Audible, sir. Audible.
Okay. Is there any doubt to you?
No, sir. No.
Knocking and, or you can say pinging. All right.
Sir, please raise your voice, sir. Speaker, sir, your voice is very low.
Okay. Okay. Let me see. Is my voice now better?
Still,
Is it?
it is low, sir.
It is low. Is it better now? Hello? I don't know. Is it better?
Yes.
Okay. Now, what is this abnormal combustion or knocking? So, what happens during the propagation of the flame front? There is a following effect on the end charge which is still here, the end charge which is kept here. Okay. So, what is happening? The air fuel mixture, which is very near to this flame front, okay, expand. Air fuel mixture near the flame front expand, and it compresses the end charge. So this flame front is basically compressing this end charge. Okay. Eventually it is compressing. So due to this heat transfer from flame front, mainly because of the radiation, there is also increase in the end charge temperature. Although what was happening, the flame fronts were traveling, they were traveling, they were compressing whatever the fuel was here. Okay. Towards the end, they were compressing, and because of that, it was already at flash temperature. But because of the compression of the flame front, these end charge temperature still got raised, and it reaches the self ignition temperature. Because of the compression of these flame fronts, the temperature raised, and because of that, these end charge temperature reach the ignition temperature of the fuel. And if there is any hot spot where we have a local temperature high region also, One reason is that because of the compression of the end flame front, the pressure temperature raised of the end charge. Another reason is there if there is any hot spot, that is a localized high temperature region, then also end charge temperature will increase. And due to these reasons, if the end charge temperature has risen greater than or equal to the self ignition temperature of the fuel, these end charge will ignite on their own. These end charge will ignite. And what will happen because of this ignition? Now, what will happen because of this ignition? Let me show. What will happen? This flame front was moving from here to here, okay, which was actually coming. But this end charge also got ignited, and because of that, this start to form a flame front in this direction. Okay, so one flame front was coming from left to right, and because of the temperature rise of the end charge because of the following reason, this flame front come from right to left. Now there is a collision between the two flame fronts, and this collision is known as knocking or detonation or pinging. Okay, and these collision provide a very high shock wave energies because these are traveling at very high speeds. We have seen that the time calculations are very fractions of milliseconds. Okay, let me write all these points. During propagation, of flame front, following effects on end charge. First, air fuel mixture particle near flame front expands and it compresses the end charge. Let us say end charge is denoted with EC. Compresses the end charge. Because of this implies temperature of end charge increases. Another reason, due to heat transfer, from flame front from FF, mainly because of radiation, temperature of end charge increases. Another reason, if there is any hot spot, that is your localized high temperature zone, then again temperature of end charge is going to increase. So what is happening? Let me make a diagram here also. This is our spark plug. Okay, we have end charges, flame fronts, which are coming, and we have a set of end charges which were here. Okay, so fuel particles which were expanding from here okay, they compresses the end charge. Okay, also they provide radiation, Q of radiation. Okay, and if suppose I have a localized hotspot zone, localized high temperature zone here, hotspot. So first compression, then radiation heat transfer, or if I have a hotspot, what will happen? A further end charge the temperature of the end charge will increase. And because of that, a flame front will opposite direction will form. Okay. So what is happening? There was a propagation from here to here. Again, there is a propagation from here to here. Okay. Of the air fuel mixture particles. So due to above reasons, if temperature of end charge is greater than or equal to its self-ignition, then separate flame front. So this is FF, this is FF. Then separate flame front will form from the end charge, and this flame front will collide with the flame front coming from spark plug, and this collision is known as knocking, detonation, or pinging. Okay. So when the collision is happening, let me make another diagram. Is my voice clear now? Is it clearly coming? Or is it still low? Guru Prasad?
Sir,
Is my voice still coming or it's low right still?
your speaker is showing 50% only, sir.
No, that is a battery symbol. I'm asking, my voice is clear to you? Okay.
Clear, sir.
Okay. So I'll make another diagram. So I have a spark plug. I have a set of end charge which was coming from here. And also I have a set of end charge which is coming from here. A flame front of set which is coming from here. Okay. This flame front is traveling here. This flame front is traveling here. Because of that, there is.
Sir, last class I have asked about numerical problems
We
which
will.
were given in
Yeah,
the
I'll come to the
assignment.
end. Yeah, I'll come to the end. Please let me finish this.
Okay.
Okay. So because of this collision, a very high shock wave energy will form. High energy shock waves will form. Okay. So if I show you again from a top view, this is my spark plug. Okay, I should not make like this. Okay, let us say like this. Okay. And from the front view, if I try to show, so this was my spark plug. Okay. Suppose this is my exhaust valve. Another end charge will form a flame front from here. Okay. All of these are the diagram. So enormous amount of energy at this point of time, and temperature of cylinder is very high. Very high. So when piston cylinder are colliding, Okay, this forms a noise that is called as a pinging noise. Okay, that is why we want to keep the spark plug towards the exhaust. Okay, because exhaust valve is a hot spot from where most of the exhaust gases are taking out. So already it is a very high temperature zone. Okay, so we need to keep the spark plug near to the exhaust. Okay, near to the exhaust valve. I'll explain all these things. So high energy shock waves forms. Let me write high energy shock waves. HESW. HESW. H. Okay, what these lead to? Collision of piston and cylinders. Piston and cylinder, which leads to vibration and noises increases. Also fatigue loading, which cause fatigue loadings, because of which rate of propagation of cracks or this is infinite, because of which failure rate increases of piston cylinder increases, this because of which life of piston decreases. Okay, because of the presence of this high energy shock waves. This is basically your knocking. Okay, which is basically the collision between frame front and flame front from end charge. Okay, this creates a metallic sound. Which is also called as pinging. Okay, because of this the indicated power also decreases. We want full combustion to happen properly in one direction, but it is happening in two ways and collision is happening. Because of that, friction power increases. Friction is happening, because of which the energy, that is heat added, is not sufficient. Heat addition not sufficient, because of which your brake power decreases, whatever power you want at the output, because of which mechanical efficiency decreases, also because of which brake specific fuel consumption decreases, brake thermal efficiency decreases. Okay, okay, all right. So this is a holistic chart, what happens because of the presence of what we call as heat energy shock wave formation, that is the presence of knocking inside the cylinder. Okay, which is not at all required. Any doubts? Now we will understand what are the factors affecting the knocking. Okay, what are the factors that affects knocking? Affecting knocking. Let's go one by one. The first one is the compression ratio. The first factor is your compression ratio, that is your R. Just give me a minute, please. I'll be back. Okay. So first factor is compression ratio. That is R. So we know that compression ratio is nothing but can be written in the form T2 by T1, which is nothing but R to the power of gamma minus 1. Okay. Compression ratio is V1 by V2, or it can be written as T2 by T1. This is a relation. So what happens? From 1 to 0.2, when the compression is happening, the temperature of the cylinder is increasing. So this implies T2 or T cylinder increases. This implies temperature of air fuel mixture is increasing, right? Temperature of during after the compression, the temperature of the air fuel mixture increases because the temperature of the cylinder is increasing. Okay. If the temperature of the cylinder is increasing, there is a possibility a hotspot can be formed, which will eventually lead to knocking. So a higher compression ratio provides a higher temperature, and because of that, knocking will be taking place. Knocking tendency happens. So that is why one reason is that SI engines or Otto cycles are of lower compression ratio. Okay, now you can understand through this way also. And because of this knocking, your brake thermal efficiency also decreases. And this brake thermal efficiency is nothing but your efficiency of engine efficiency. Now the question can comes, we know that Otto cycle has an efficiency 1 minus 1 by R to the power of gamma minus 1. If we increase R, our efficiency is also going to increase. Okay, but when we are increasing R, our brake thermal efficiency is decreasing. So when the examiner is trying to ask how the compression ratio is going to impact the engine efficiency, then you can't say about the Otto cycle. Otto cycle efficiency is an idle cycle efficiency. You have to talk about the brake thermal efficiency at that point of time. Then you have to explain the compression ratio concept through this way, that it will increase the knocking tendency and which will reduce the engine efficiency, okay, by increasing the compression ratio. Because Otto cycle efficiency is nothing but your air standard efficiency, okay, which is an idle, but it's not an engine efficiency. And if the temperature of the end charge increases, then eventually your charge delay, the time from A to B, is going to decrease. If the temperature of the end charge increases, that means your charge delay decreases. That means it reaches immediately to self-ignition temperature, which leads to knocking once again. Okay. So according to Otto, efficiency will increase with the increase in compression ratio. But engine efficiency is going to decrease. That is why we have to keep the Otto cycle compression ratio between 6 to 12. That is why R of Otto cycle between 6 to 12. It cannot be more than that. One reason is this. Okay. That is why designer, who is the engine design in the R&D team of any of the automobile industry, he or she should always keep the compression ratio in this range for the IC engines. Okay. So because R increases, Otto cycle efficiency increases, but that means the load carrying capacity increases. That means the torque is increasing. That means your temperature is increasing inside the cylinder. That means your knocking tendency is increasing. That means your engine efficiency is decreasing. You can understand through this way as well. Next point is, this one was compression ratio. Second will be RPM of the engine. So engine speed. If I say N, if I'm increasing N, if I'm saying if my speed of the engine is increasing, that eventually means the turbulence inside the engine is increasing. turbulence is increasing. And if somewhere turbulence increases, that means the convective heat transfer from the hotspot to air-filled mixture will also increase. Convective, not radiation. Convective mode of heat transfer. Convective heat transfer from hotspot to air-fuel mixture will increase. That means basically what I'm saying, there is a temperature for an air-fuel mixture, okay, but it is not greater than the self-ignition temperature because the fuel is, there is a higher speed, the fuel is pumping at a very, air-fuel mixture is pumping at a very higher speed, turbulence is being involved inside the cylinder, which leads to convective heat transfer increment of the air-fuel mixture and which reduces the temperature of the end charge. Okay, so we can say that temperature of the hotspot decreases, temperature of hotspot decreases, and because of that, the temperature of end charge decreases. Because of that, knocking tendency decreases. Okay, so that is why when we say a IC engine spark ignition engine has a power of formula that is torque into omega. That is why the spark ignition engine are run at a higher speed and lower torque. Okay, so omega is high for a spark ignition engine, but torque is less. For same power output generation between a CI engine and SI engine, the omega of a SI engine is higher compared to the CI engine. So another factor is this also eventually reduces the knocking tendency. Knocking is not a good thing. We want to reduce it. Okay, so that one reason is that compression ratio should be between the range, not very high, and the engine should have a higher speed. Okay. Next point is load over the engine. Load over the engine. Third, load. The passenger carrying capacity basically. If you increase the load, the car is made for like car or bike is made for 2 or 4 persons. Okay, and you are putting 6% or 5%, you are increasing the load over that vehicle. Similarly, a bike or two-wheeler is made for 2 persons, you are increasing by sitting 3 or 4 persons, then you are increasing the load over the system. So by increasing the load, that means you want more fuel supply to carry that load by the engine. Okay, that means heat addition is also going to increase because more fuel you are supplying, heat is increasing. That means temperature of the cylinder is going to increase. Temperature of cylinder is going to increase. Or you can say temperature of hot spots is also going to increase. What they will do? They will increase the temperature of the end charges. They will cause knocking. So you might have heard if a vehicle has been used for a quite long amount of time and you guys more than required passenger capacity, you go in a SI engine, you will see a car after some time or a bike after some time will start making noises. Okay, which is not good. Okay, that will lead to knocking tendency increasing. Okay, that is it is not advice. But in CI engine it is opposite. We will discuss that. Don't worry. Fourth is inlet air fuel mixture temperature. Okay, if I am providing the air fuel mixture itself at a higher temperature, if I increase the inlet of AFM at a higher temperature, this eventually means my hotspot temperature is also going to increase. This means my knocking is also again going to increase, which is not required. Okay, so our inlet valve and how the temperature of the inlet will increase. One way is that if the temperature of the inlet valve is itself high. Okay, that is temperature of inlet valve is high. then the temperature of inlet air film mixture is going to increase. Okay. So that is why supercharging is performed. I'll explain what is supercharging later, but supercharging is better in CI engines because you want that at higher temperature the air should be mixed. Okay, but it is not performed in the SI engines because they will increase the hotspot temperature. Next is what can be the position of a spark plug? Fifth factor. Location of spark plug. Where should I put the spark plug? In the center, left, near to the inlet valve, or to the exit valve, or in the middle? So let us say I put, this is my center line, I put near to the inlet valve. Okay, spark. So how the flame fronts are going to travel? Okay, and the end charge is coming from here. Hotspot region is your exit valve, exhaust valve. If I put another scenario where I have spark plug exactly in the middle, okay, so my flame fronts are like coming from the center, and here from the exhaust valve, the end charge flame front is coming. Another case can be if I put near to the exhaust valve. So my flame front will be like this, and this will be flame front from the end charge. Now we can visualize that if I put near to the exhaust valve, the flame front from the spark is traveling very fast and it is near to the end charge. And it won't give much amount of time for the end charge flame front to travel. Instead of, if my spark plug is towards the left side, the first case, then what will happen? My flame front from the end spark plug is taking longer amount of time to travel towards the exhaust valve, and meanwhile it will give the time to the end charge to cover also, and which will create more amount of flame fronts, and that can collide more. That is why it is always suggests that the location of the spark plug should always be near to the exhaust valve, should always be near to the exhaust valve, near to exhaust valve. That will reduce spark plug location near to exhaust valve, that is this case, decreases knocking. Okay, decreases knocking. And if you heard one of the organization, I don't remember the name, they have, I think Bajaj is there. If you heard one of their bikes called as Pulsar, they got a twin spark ignition. That was a patent. That instead of having one spark plug in a cylinder, let's have two spark plugs and aligned at a particular position, which will eventually won't allow end charge flame front to form. Okay, let me show how. So, and this was their patented technology. They could have ever thought at that time. Okay, so they installed two spark plugs, and you have heard the bike names with twin spark ignition, and flame fronts travel in such a way, it forms the flame fronts in such a way that it don't allow the end charge to form itself, end charge flame front to form. So this is called as twin spark, twin sparking. Okay, and this reduces the travel time of flame front. This implies travel time of flame front decreases. Okay, so our flame front that is coming from the spark plug is moving very fast, and the time is very less, and this leads to knocking equal to 0. This eventually eliminated the knocking. Okay, That's why they have patented this thing. Next thing is, sixth factor is length of flame travel. So if you see that you are saying the length of this flame travel, it should have some particular length. If length is very high, then it is going to take longer amount of time to reach the exhaust wall or a hotspot, and it will immediately ignite the end charge, and that will form a flame front which will cause knocking. So that is why we can't have a cylinder diameter to be very high in a SI engine. That is why you see that in a SI engine you have a 3-cylinder or 4-cylinder. The engine is of 3 or 4 cylinders. Okay, so that is why petrol engines diameter or bore is less than equal to 12 centimeter, and it is multi-cylinder. Because if I make a diagram to show you, if my cylinder is smaller and if my cylinder is bigger, okay, my spark plug is like this. Here the end charge is here, suppose end charge flame front is here, and here also. Time taken for a smaller diameter flame to travel is less. Length of the flame traveling will be less compared to this. Will take large amount of time to travel. Okay, so that is why it will increase the knocking tendency. So here we can say that time travel for flame front decreases. That means length of frame front decreases. That means time travel to flame front decreases. That means knocking decreases. Okay, so this is a case of D 12 centimeter. Okay, but now the question will come that more than one cylinder is there, and this also solves another problem. When I told initially that we have a flywheel which is attached to the crank, but when instead of flywheel, when we do more than one cylinder in an engine, then the other cylinder and the firing is not happening at same time for all the cylinders. There is a firing order also, which I will tell in the later tutorials. Then what happens when the one cylinder is getting fired, the other cylinder is storing the energy. So that means that piston cylinder is acting as a flywheel for the other scenario. Okay, so there is no need of a flywheel also. Okay, and by increasing the amount of cylinders for a small cylinder size, you can cover the same swept volume. Okay, if we say that our engine is 1.2 centimeter cube, sorry, 1.2 cc engine, okay, cubic centimeter. So then we can say that my whole engine is 1.2 and I have 4 cylinders, then each engine is of 0.3 cc. Okay, so that is why the bore of a petrol engine is restricted to 12 centimeter for the better performance by reducing the knocking tendency, thereby decreasing the time for flame front to travel to reach the end charge before the self-ignition temperature of the end charge. There is one note point I want to mention towards the end. The temperature of the end charge and temperature of self-ignition, there is a chemical delay, right? If this chemical delay of the end charge increases, that implies time travel to flame front will TTFF. This is nothing but TT, time travel to for flame front. TTFF is going to of the end charge will. If charge delay is increasing, then time travel for flame front of the end charge will increase. Okay, which is a favorable condition. We want that the flame front of the time for the flame front to form for the end charge should be less. Okay, that means your self ignition temperature will increase but at a later point of time. So we can say that knocking is going to decrease. And how we can have a fuel which is of a higher self-ignition temperature? We can have different types of fuels whose self-ignition temperature is high. If the self-ignition temperature, one fuel is at one fuel has a self-ignition temperature of 120 degrees Celsius, other has 140, and another has 200. So 201 is better because it takes more amount of time to uh, chemical action to happen. That will increase the charge delay, and that will not allow the end charge to immediately burn or ignite. Okay, so there are three kind of fuels: aromatics, olefins, or paraffins. Okay, so aromatics are basically the chain formed fuels. Okay, aromatics, these are CnH2n-6. These are aromatics. They have a higher self-ignition temperature compared to a hydrocarbon chain that is combination of single and double bonded. Okay. What did I make? Two bonds here. Okay. H, 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 H. So I have a double bonded chain. These are called as alkene alkynes. These are olefins. Okay. Alkenes or alkynes. And these are olefins. And the self-ignition temperature of these are higher than the alkanes. Those are single chain structures. Okay. There is no double chain structure. So to break the bond for ignition, it will take more amount of time for chain formation to break compared to a single stranded structure. So alkanes. And these are called as paraffins. Okay. So these are, we can say that if self-ignition temperature of fuel is increased, this implies charge delay will increase. This implies knocking will decrease. So that is why alcohol is mixed in a fuel to increase the self-ignition temperature also. Okay. Okay, I think we can stop here. It's already time. We have seen in detail combustion in the SI engines with first and second stage combustions and factors affecting the knocking. Probably next tutorial will start with the CI engines. So I hope everyone was able to understand the lecture. It's a bit more of theoretical, conceptual. For explaining each and every stage is very important. If you are, I hope that everyone is regular to the lecture videos by the professor and tutorials as well as the assignments. So those you also get the assignment solutions. Other thing is that I hope that everyone probably will be attending the exam as well. We are in the mid of our course now. Almost six of the tutorials have passed, including this one, and you are able to access these tutorial recordings and the PDF sheets, which are sent by a NPTEL team in a form of a Google Sheet, as well as those who are new and watching through YouTube. So you can also watch my lecture videos on my YouTube, whose channel name is NPTEL with Varnit, where I upload all these recordings with Varnit. And in the corresponding course, you have videos by week wise, and each video description there is a, you can say, a link of a Google Drive where you will get the PDF of these notes. All right. I think let me stop the recording and we can end the session.